Geometry, Unit 5, Chapter 7, Section 1, Transformations and Symmetry. Translation is when the object is moved around on the x and y axis. The position of the object is changed, but nothing else about it is. So this is a translation. See how the object is just moving around the x and y axis, but nothing else is changed about it. It's just moving on the x, it's moving on the y, so it's just moving around. That is a translation. So let's look at how we can do a translation on a graph and change its x and y position by the same amount. So the translation we're going to be doing is x minus 5, y plus 2. Here's all my original points here, 1, 1, 1, 4, 4, 1. So I apply the translation to 1, 1. So 1 minus 5 is negative 4. 1 plus 2 is 3. So let's graph that. Negative 4, 3. 1 minus 5, negative 4. 4 plus 2 is 6. So negative 4, 6. 4, 1. 4 minus 5 is negative 1. 1 plus 2 is 3. So that is my translated object. Now, also, if I have letters here, A, B, C, when I translate it, it becomes A prime, B prime, C prime. The translation here can also be represented as a vector, like this, negative 5, 2. So that's doing the same thing, x minus 5, y plus 2. That's it as represented as a vector. Reflection. The reflection is when the reverse of an image across a line. So usually we're going to be doing around the x-axis, the y-axis, or the line y equals x. So when my image here gets reflected, what I look at is I look at this distance. And I'm going to have that same distance repeated over here. So this distance, and then you can see here this top distance. And so the image gets reflected across the line. Same idea as before. If this is A, B, C, this becomes A prime, B prime, C prime. Now let's do it on x and y axis. So we're reflecting across the x-axis. So we're reflecting across this line. So I'm going to look at the distances. The distance of 1, distance of 1. Distance of 1, 1. Distance of 3. There is my image reflected across it, the x-axis. So negative 2, 1 became negative 2, negative 1. Negative 1, 3 became negative 1, negative 3. And then negative 6, negative 1. You'll notice when we reflect across the x-axis, the y changed from positive to negative. Again, A, B, C, A prime, B prime, C prime. Now let's reflect across the line y equals x. So I'm reflecting across this line. I'm going to do the same thing I've been doing. I'm going to look at this in terms of distance. So I'm going to find the distance from the point to the line. And what I'm going to do is I'm going to do it going on the x and y. So I went over 2, down 1, so I'm going to do the same basic idea. And what I'm going to do is I'm going to reflect it now in the opposite fashion. Over 1, down 2. Over 2, down 2. So over 2, down 2. And then this one, that's over 6, down 1. So over 1, down 6. And there is my reflected image across the line y equals x. A prime, sorry, that's going to be A, not A prime. A, B, C. So A prime, C prime, B prime. So negative 2, 1. This became 1, negative 2. Negative 1, 3 became 3, negative 1. And then negative 6 became 1, negative 6. So you'll notice what happened when reflected across the y equals x is your coordinates just flipped. Your x and y just flipped positions. Let's look at rotation. Rotation is an object that's turned about a point. Usually we do 90, 180, 270 degrees, but we can do other measurements. So all we're doing is we're rotating the image. That's a rotation. So let's look at a 90-degree rotation. It's fairly easy to remember. All we're going to do is we're going to flip the x and y axis. So x, y comes yx. We're just going to also be aware of where the negative signs go. So if I'm doing a 90-degree rotation, this point's going to end up in this quadrant. That means your x and y will be negative. This point will end up in this quadrant, so it's x will be positive, but the y will be negative. Same with this point. So easy way to remember it, like I said, it's a change in the x and y, but we got to keep track of the x and y values. So I'm going to think about this. 3, 2 becomes 2, 3. This will become 1, 4. This will become 3, 1. But I also have to think about the negatives. So 3, 2, that's this guy. He's going to be now 2, 3 in this quadrant. So the 3 is negative. 1, we've got 1, 3. 1, 3 will become 3, 1 in this quadrant. So the 1 is negative. And then we've got the 4, negative 1. 4, negative 1 will be over here as 1, negative 4. So there is our rotated triangle, and those are both negative. So I'm going to label this A, B, C, A prime, B prime, C prime. And there we go. That's a 90-degree rotation, clockwise. If I'm going counterclockwise, it's in this direction. Dilation. Dilation is an enlargement or a shrinkage of an object by a scale factor. So if my original triangle is here, I increase it by 2 times, and I get this. But if I half it, I get the shrinkage. So dilation is just increasing or decreasing your size of your original object. So if I do a scale factor of 2, I just, about the origin, about 0, 0, all I have to do is multiply by numbers by the scale factor. So 2 times 0, 2 times 0, 2 times 2, 2 times 0, 0 times 2, 2 times 2. And here is my new image. So A, B, C. So A is also A prime, B prime, C prime. So there's my scale factor of 2. Line symmetry is the idea that a shape can be folded in half and each side, as it gets folded, overlaps each other. So if I fold this shape along that dotted line, this side here ends up getting folded right on top of it. So it has line symmetry along that line. But I can't just fold it any place I want to. If I try folding it here, what happens is this ends up looking like this. So it's not folded on top of it. It doesn't have line symmetry there. It only has line symmetry along that dotted line. So how many lines of symmetry exist for this regular pentagon? Well, let's find out. I can fold it here. I can fold it here, 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 and here. That's 5 lines. That's 5 lines. So every regular polygon has lines of symmetry equal to the number of sides. Remember, regular polygon means all sides and all angles are congruent. So I said this is a regular pentagon, thus is 5 lines of symmetry. Rotational symmetry is the idea that an object can be rotated x degrees and still be in its original shape. Well, if I rotate the square 90 degrees, oh, it still looks the same. So a square has 90-degree rotation. An octagon here, look, I can rotate it. Oh, still the same. Still the same. An octagon has 45-degree rotation. Now, question is, where did I get these? 360 divided by 4 sides is 90. 360 divided by 8 sides is 45 degrees. So all regular polygons have rotational symmetry, and it's 360 divided by the number of sides. Point symmetry is the idea that an object can be rotated 180 degrees, and the object will be completely overlapping its original form. So if I rotate this shape 180 degrees, the sides will overlap. Again, 180 degrees, and this will be overlapping. Not all shapes have point symmetry. Not all regular polygons have point symmetry either. Only the even-sided regular polygons have point symmetry. And that is the end of this lesson.